Hey everyone, welcome back and let's write some more neat code today. So today we're going to solve longest repeating character replacement. And so this is another problem from that blind 75 list. So we are going to be one step closer to completing the entire list. The link will be in the description to this spreadsheet if you do want to take a look. And hello to the 6 people that are currently viewing the spreadsheet right now. You're going to be in the next video. But okay, so let's get into this problem because it's another pretty fundamental problem that's really good to understand. So we're given a string s and a single integer k. And so basically they tell us that we can choose any of the characters in the string and change it to any other uppercase English character. So in this problem, every character in the input string is going to be limited to uppercase English characters, and we know that there's 26 uppercase English characters from capital A to capital Z. And so basically we can perform a replacement on any of the characters at most k times. So we're allowed to replace k different characters in the string to any other character we want. And what we want to do is return the length of the longest substring containing the exact same character we can get after performing at most k different replacements. So we just want to return that length. We don't actually have to make those replacements in the input string. So in this case, when we take a look at the input string, we have AB, and we're allowed to replace 2 of the characters. So what's the longest substring we could get with the exact same character? Well, we could replace one of the B's. We could basically replace both of the B's with a capital A, and then we get 4 A's in a row, which would give us an output of 4. And we could technically also do the opposite. We could replace the A's with capital B's, and that would give us the exact same result, a length of 4. So I'm going to show you how you can solve this problem in big O of n time, and technically it's going to be big O of 26 multiplied by n, which we know is also reduces to big O of n, but there's actually technically an easier way to do it, or at least a more simple way to do it, which is just going to be a flat big O of n. We don't even need this 26 constant. But this way is actually pretty tricky to get to, so I'll be going over a little bit of it, but this is kind of the main way that you'd want to solve this problem. So let's say we're given an input string like this, and we're given a k value. Now the most brute force substring in the entire, every single substring, right? And And if we were checking every single substring in the entire input array, we know there's n squared substrings, so that wouldn't be the most efficient way to do it. But even if we were doing it like that, what exactly are we looking for? If we're looking at a particular substring, how do we know if this substring is valid? Because remember, at the end of the day, we want to maximize the result, right? The result is going to be the longest substring that contains a single character, and we can make two replacements. So let's look at this substring alone. How do we know if it's valid? Well, which character are we going to replace? Are we going to want to replace the B's in order to make it all be to match A? Or would we want to replace the A in order to match it with the rest of the B's? Of course, we're going to replace the character that occurs less frequently, right? Because the number of replacements we have is limited, so we would want to replace the characters that are less frequent. So in other words, we want all characters in a particular window to match the most common character in that window. So what we're going to be doing is we are going to have a hash map or a array, which is going to take every single character. In this case, we only have characters A and B, and we're going to count the number of occurrences of each character. So for example, if we were looking at this substring, we see that there's 3 B's and we have a single A. So how do we know if this window is valid? What we're going to do is we're going to take the length of the window, which is going to be 4, right? We're going to take the length of the window, right, which we know in this case is 4, and we're going to take the length or the count of the most frequent character. In this case, we know that that's B, and the count of it happens to be 3, so we're going to take 4 minus 3, and from that, we're going to get a 1. Now, what does this value 1 tell us? It tells us the number of characters in our window right now that we need to replace in order to make it match the most frequent character B, right? We have a B here. We want everything to match a B. In this case, we only have an A, right? But it could be possible, like, who knows, maybe that we would have a C over here, right? Or an X over here. And it doesn't really matter what the characters are. We just know that B is the most frequent character in the window, and the other characters that are not B, A and Z, for example, are the characters we want to replace. So we can calculate the number of characters we want to replace just like this. And so we want to replace one character. How do we know if we have enough replacements to do one character? Well, of course, that's our input parameter k, right? So what we're confirming here is that this value is less than or equal to k. As long as this condition is true, that means our current window is valid. That means we have enough replacements to make those replacements in our current window. So this is the main condition that we're going to be checking. The other question is, how are we going to know which character is the most frequent? Well, the brute force way is going to be taking a look at our map of counts, and we know that the max size of this could possibly be 26 because we'd only have 26 different characters. So finding the max character is going to be big O of 26, so that's a little bit more inefficient than we would like, but it's technically still linear time. Like, the overall algorithm is still going to be linear time. The last thing that we're going to have to do, though, is to this equation, we're going to have to add a sliding window technique. So basically what we're going to do is we're going to take our window, start at the beginning, expand it as much as we can, as long as the condition that we mentioned is valid. If the condition is not valid, then we're going to take our left pointer and then shift it as well until the string becomes valid once again. So we're going to have a left and right pointer. So initially left is going to be at the beginning and right is also going to be at the beginning. And also the counts of A and B are initially going to be 0. Now we're going to look at the first character, right? That's where our right pointer happens to be. We're going to look at it. We're going to say, okay, we have a single A, right? We're going to take our count of A and set it to 1 now. So is this window valid? As in, can this window be the exact same character within 2 replacements? Of course it can, right? That's kind of the trivial case, but we would still calculate it. And the way we would calculate it is get the size of our window. Right now we can see the size of our window is 1, subtracted by the count of the most frequent character. In this case, we know the most frequent character is A. 1 minus 1, is that greater is that less than or equal to k? We know k is 2, so of course this is going to equal 0. 0 is less than or equal to 2, which is k, right? So of course this window is valid. That's kind of a trivial case. Next, we're going to shift our right pointer to the next character, right? So now we have a b, so we're going to increment the count of b in our map. So b is now going to be set to 1. In this case, the length of our window is 2. The most frequent character is either of these, right? And the count of that frequent character is going to be 1. So we're going to get 2 minus 1 equal to 1. So this is the number of replacements that we would have to do. And looking at our current window, that makes sense, right? We'd have to replace at least one of these two characters. So we're going to ensure that the number of replacements that we need to do is less than or equal to k, which is 2. Of course, that's true. So our window is currently valid. I guess I did forget to update our result. So since this window is valid, the length of the window is going to be set to the result, right? So right now the result is 2. 2 is the length of the longest window that we can get. So that's our result for now. So now let's continue. Next, we're going to shift our right pointer to the third character. So now we get another a. So we're going to take the count of a and increment it all the way to 2. And we're basically going to repeat our algorithm. So once again, we're going to get the length of the window 3 minus the count of the most frequent character. We see the most frequent character is a. So the count of it is 2. 3 minus 2 is 1. Is that less than or equal to 2, which is k? Yes, of course it is. So this window is also valid. We can update our result now to 3. So we found another window even longer. So I'm going to take our right pointer once again and then shift it over to the b. So now we're going to be, since we reached another b, we're going to increment the count of b to 2. Also 2 is 1. Is that less than or equal to 2, which is k? We found, and then shift it over to the b. So now we're going to be, since we reached another b, we're going to increment the count of b to 2 now. And so the length of our window now is 4, and the count of the most frequent character is either of these, and that's going to be 2. 4 minus 2 is equal to 2. Is that less than or equal to k? K is 2 in this case. So of course, once again, this condition does hold. So once again, we found a window that's longer than our result. We found a window now of length 4. And so once again, we're going to take our right pointer and shift it. So now another b. Let's increment the count of b to 3. So the length of the window now is 5 minus the count of the most frequent character. That character is b. 5 minus 3 is this 2, and less than or equal to k. Of course, it's still true because when you look at our window, we have 3 b's. So that means we're going to be replacing the a's. So we're going to need to make 2 replacements, and we are allowed to make 2 replacements. Okay, so now we're finally going to get to the case that I mentioned earlier where we're going to have to take our left pointer and then slide it to the right, which is why this is a sliding window problem. So now we reached an a, so we're going to take the count of a and set it to 3. So now we have A count 3 and B count 3. So let's take the size of our window, 6, subtract from it the count of the most frequent character. It's going to be either of these, so 6 minus 3 means we need to make 3 replacements. Is that less than or equal to k? K is 2, so we exceeded k, right? We exceeded the number of replacements we're allowed to make. If we wanted this window to be valid, we have to replace 3 characters in it, but we're not allowed to do that. So what we have to do is shrink the size of our window until we are valid. So we're going to take our left pointer and shift it to the right. So now the left pointer is going to be over here. It's going to be at the B. So since we removed this A from our window, we have to decrement the count of A in our window. So I'm going to cross this 3 out, and now it's actually going to be set to 2. I kind of ran out of room, but I hope this is still readable. So now the count of A is 2. So now let's once again check, is our window valid? Well, the size of the window now is 5, and the count of the most frequent character is B, and that's going to be 3. So 5 minus 3 is going to be equal to 2. Is that less than or equal to K? Yes, we are once again valid. So this is technically a valid window, and I think I forgot to update the result earlier when we had a window of size 5. So the result right now would be size 5 because the longest window we can make is either this window or the window that we had earlier with these first 5 characters. But yeah, and so at this point we would stop our algorithm because we did find a window of 5 that is valid, and our right pointer cannot be shifted anymore. So this is the general algorithm. So it's a basic sliding, it's a fundamental sliding window problem with this particular condition being important. But there's actually one way you can do it without having to look through the entire hash map every time you want to find the most frequent character that occurs. And it's kind of tricky to arrive at this solution, but it's pretty easy to implement once you can figure it out. I'll explain the algorithm at a high level. I don't want to waste too much time on it, but basically we're going to be having another variable, and it's going to be called max frequency, basically the count of the most frequent character at any given time. So basically, for example, if we had A as a count of 3 and B as count 2, we'd say, okay, the count of the most frequent character occurs 3 times, so max F is going to be 3. And so anytime, if we got a B, let's say we incremented our B all the way up to 4, then we'd want to update our max frequency to 4, right? So we'd always want this to be the most frequent character. Now, the one problem is if we're trying to maintain the count of the most frequent character, what happens when we take our left pointer, for example, right, and then shift it, right? When we do that, we're basically removing a character, and therefore we're going to have to update our count map, right? We are going to do that. And if that does happen, right, let's say we took B and then from 4, we decremented it all the way down to 2, for example. Then we'd have to rescan this entire map and then find, okay, what's the new most frequent character, right? So we'd have to take our max frequency and from 4 downgrade it all the way to a 3, for example. So then we'd have to set it to a 3, and that would basically defeat the purpose, right? We'd still have to do that big O of 26 calculation to scan through this, but it's technically true that you don't have to decrement this max frequency. But the main idea is this. The result is only going to be maximized as we find a new max frequency, right? Because remember what we were doing. We were taking the length of the window subtracted by the max frequency, right? Whatever the most occurring character was, and we wanted to minimize this, right? So basically we want the length to be maximized because that's what our result is going to be set to. So therefore, we also want the max frequency to be maximized because we want to ensure that this is less than or equal to K, and K is going to be a constant. So for example, let's say I had a max frequency of 4, but let's say now the new max frequency got downgraded to a 3. I'm still going to leave this as a 4 because it's not going to change our result. Because for example, if I had a 6 minus 4, that was less than or equal to K, which is 2 in our example. And if I leave this as a 4, I'm basically overestimating what the max frequency is, but we know at least at one given point in time it was a 4, so therefore we were able to take the length 6 and then set it equal to our result. And now, so let's say our result is now 6. If we're ever going to increase the result from 6 to another number, like for example 7, we would require our max frequency to increase. If it stays the same or if it decreases, our result is never going to change because we only change our result when we increase our max frequency because that's the only way this condition here is going to be true. So If our max frequency is downgraded, we don't have to actually update it. We don't have to look through the entire hash map to find the new max frequency. But if we increase our max frequency, for example, if I took this A and then from 3 I set it equal to a 5, then that's something we can check in big O of 1 time. And then if we increase this, then we definitely do want to update our max frequency and increase it. And that's something we can do in big O of 1 time. So I know I probably went a little too long into this, but the main idea here I'm trying to get at is the easy way to solve this problem with a sliding window is going to be big O of 26 times n, which is technically linear, but there is a clever way to do this in big O of n time that honestly I didn't figure out on my own, and I wouldn't really expect other people to be able to figure it out on their own, like in an interview at all. But I will show this, the standard solution, and I'll also show the code for this more optimized solution. Okay, so now let's jump into the code, and the code is actually a lot easier than the visual example that I gave, a lot shorter for sure. So we're going to have a hash map to count the occurrences of each character, and we're also going to have a result, which is going to tell us the longest substring that we can create with k replacements. And we're going to have a left pointer, which is going to be at 0, and then our right pointer is going to go through every single position in the entire string S. So what we're going to do is for the character at position R, we're going to increment the count of it. We're going to take 1 plus whatever the count currently was, count.get this character. And if the character doesn't exist in our hash map, we're just going to return a default value of 0. That's what this function is doing. And so before, what we're going to obviously do is update our result, right? And we want to set the result equal to the max that it's ever been and set it basically equal to the size of the window. We can get the size of the window. So we're going to take the max of result and the size of the window. The size of the window can be gotten with right minus left plus 1. But before we do this, before we update the result, we want to make sure that the current window is valid. So what I'm going to do is basically say while, and I don't think you would actually need a while here. You could just do if, but I'm just going to do while just because. So while the window is not valid, and we would know that by taking the length of the window, which we have down here, so I'm just going to copy and paste that, the length of the window subtracted by the count of the most frequent character, which can be gotten with max of count dot values. Right, we're basically going through the hash map, which could be size 26, and just getting the max value from it. So this is the number of replacements that we have to do, and if the number of replacements was greater than the number of replacements that's allowed, which is equal to k, that's when we would want to shift our left pointer. So we'd want to increment our left pointer. But before we increment the left pointer, we'd want to take the count of the character at the left position and then decrement it by 1. And that is the entire algorithm. After
What? How? SL equals.
And as you can see, this is pretty efficient. It's linear time. It's about as efficient as you would need, I think, but I'm going to make that slight optimization that I showed you. I'm going to maintain the max frequency in a single variable so that we won't have to do this operation where we're getting the max of the entire hash map. Instead, up here, before we execute that loop, I'm going to say max frequency is going to be equal to the max of what it currently is, max frequency, or it's equal to the frequency of the character that we just added a value to. Maybe that character became the most frequent character, so we would have to update our max frequency, and we can do that just like this. And this is a constant time operation. We're not scanning any list or anything. And then once we have this max frequency, we can use it in this loop execution, right? So we can replace this and just use max f for that. And the thing is, notice how even when we're shifting left, we're incrementing the left pointer, we're potentially removing characters from our window, we're still not decrementing max f because we actually don't need to. It won't end up affecting the result if we just don't decrement it. And that very slight optimization, which is really simple in terms of code, but it's kind of hard to see why we're allowed to do that. And watch how much more efficient it makes our algorithm. So as you can see, look, it definitely improved it. I think it was 50 milliseconds difference. So this is significantly faster. It's hard to see why, though. I would definitely not expect most people to be able to figure that out. So I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. Thanks for watching. Hey everyone, welcome back. Size 26 and just getting the max value from it. We're just going to return some more. What we're going to obviously do is update our result, right? And we want to set the result. Hey everyone, welcome back, and let's write some more neat code today. So today we're going to solve longest repeating character. Hey everyone, welcome back, and let's more optimized solution. Okay, so place character at position R. We're going to increment the count of it. We're going to take 1 plus whatever the count currently was, count.get this character. And if the character doesn't exist in our hash map, we're just going to return a default value of 0. That's what this function is doing. And so before, what we're going to obviously do is update our result, right? And we want to set the result equal to the max that it's ever been and set it basically equal to the size of the window. We can get the size of the window. So we're going to take the max of result and the size of the window. The size of the window can be gotten with right minus left plus 1. But before we do this, before we update the result, we want to make sure that the current window is valid. So what I'm going to do is basically say while, and I don't think you would actually need a while here. You could just do if, but I'm just going to do while just because. So while the window is not valid, and we would know that by taking the length of the window, which we have down here, so I'm just going to copy and paste that, the length of the window, subtracted by the count of the most frequent character, which can be gotten with max of count dot values, right? We're basically going through the hash map, which could be size 26, and just getting the max value from it. So this is the number of replacements that we have to do. And if the number of replacements was greater than the number of replacements that's allowed, which is equal to k, that's when we would want to shift our left pointer. So we'd want to increment our left pointer. But before we increment the left pointer, we'd want to take the count of the character at the left position and then decrement it by 1. And that is the entire algorithm after all. of the character at the left position. Hey, something we can result equal to is know that by taking hey everyone, the character placements that we added a value to. Maybe that character became the most frequent character. So we would have to update our max frequency, and we can do that just like this. And this is a constant time operation. We're not scanning any list or anything. And then once we have this max frequency, we can use it in this loop execution, right? So we can replace this and just use max F for that.